Sponges are meant to help us clean dishes and other household items efficiently every day. However, we commonly waste a lot of soap trying to get rid of messy grease and oil stains. At the same time, these sponges cleansing the products we eat from can hold water, which leads to mold growing and the sponge developing a bad smell. The aim of these experiments was to evaluate the capabilities of conducting polymers to specifically absorb different solutions based on easily doping and dedoping the sponge to manipulate its hydrophobicity. In the household, where harsh chemicals exist every day, we aim to make a sponge that can soak up oil to reduce our use of soap and soak up less water so that it dries faster and has a longer lifetime. In addition, this sponge was shown to be compatible with other organic solvents, such as those contained within a common Sharpie. Polyaniline was polymerized on simple kitchen sponges by combining APS and aniline in an HCl medium. Another sponge was made by soaking it in a pre-made polyaniline solution. Both sponges were soaked overnight and then rinsed in DI water and dried with a blow dryer. To increase the affinity of sponge for hydrophobic solutions such as oil, we doped the sponge by holding it over an ammonia solution and exposing it to the vapors. We observed the sponge turn from dark green to dark blue.
First, we measured the resistance of the sponges to verify the presence of polyaniline from our reactions. The control sponge resulted only in an overload signal from the multimeter, indicating that the resistance was too high to measure. The resistance was significantly lower for the sponge that was present in the polymerizing solution than that soaked in the pre-made polyaniline, which verified that this was the best method. Then we tested the water absorption of the sponges. As you can see, the regular sponge soaked up much more water than the dedoped sponge. This means that the dedoped sponge is indeed more hydrophobic. Next, we wanted to see if the dedoped sponge would be more effective in cleaning up cooking oil than a regular sponge, since the act of dedoping the sponge increases its hydrophobicity. We let each sponge soak in a small oil water bath for 10 seconds, and then squeezed it out to see how much oil it absorbed. The dedoped sponge soaked up much more oil than the regular one. Another test of the dedoped sponge was to remove permanent marker from non-porous surfaces. The regular sponge holding water and oil had no effect on the Sharpie on the plastic, while the dedoped sponge holding water and oil removed the Sharpie completely. Overall, the sponge demonstrated efficacy in separations applications with a higher affinity for hydrophobic solutions when dedoped. This has numerous uses within and outside the household, but may also be used in other applications by modulating the dopant or the doping concentration.